So the gamma function, it's one of those chef's kiss in mathematics, because we're going to use it to define the Laplace transform and also to evaluate some improper integrals, that otherwise it would take forever to evaluate them. Let's see how far we can get about this. Okay, so we're going to define the gamma function. We're going to evaluate the proper integrals and compare and compute values of the gamma function. Okay, guys. Well, so the gamma function is one of those special functions that occur in applied mathematics and sometimes in pure mathematics. And well, this gamma function, gamma of n, it's the integral from 0 to infinity of t to the n minus 1 e to the negative t dt. All right. Actually, this gamma function, its properties actually characterize the factorial function or the factorial of a number. All right. Well, let me actually show you the proof of this improper integral, so you can actually see how this relates to the factorial. Okay. So number one, gamma of n plus 1, that's n times gamma of n, and also gamma of n plus 1 is equal to n factorial. So I'm going to compute gamma of n plus 1. Okay, so I'm going to replace this n with an n plus 1 shortly. All right, so this will be, okay, gamma of n plus 1 equals to the integral from 0 to infinity of t to the, I'm going to replace again n with n plus 1 minus 1 from the formula, e to the negative t dt. Okay, so this will be t to the n, e to the negative t. Wait. I'm getting ahead of the game. No, this is the integral from 0 to infinity of t to the n, e to the negative t dt. Any ideas how to evaluate this integral? Hmm. How about by parts, okay? Where, remember LIATE? LIATE is the acronym used to get the first choice of u. Do we have any logarithms? Do we have any inverse tricks? Do we have any algebraic functions? The t to the n, that's our u. So u equals t to the n. That means du equals to nt to the n minus 1 dt, okay? And that means dv equals to e to the negative t dt, where v would be negative e to the negative t. All right? So the value of this integral will be u times v, okay, the integral of u dv will be u times v minus the integral of v du. That's how we evaluate. That's a formula for integration by parts. All right, so this will be u times v, that is negative t to the n, e to the negative t, okay, um, minus the integral from 0 to infinity. Well, actually, technically, this already goes between 0 and infinity, right? Because this is already a result of the integral. And then minus the integral of v, which is negative e to the negative t, times du, which is n, t to the n minus 1 dt. Okay? Let's simplify things a little bit first. Okay, so the first term remains negative t to the n over e to the t from 0 to infinity. Okay? Minus, that's a plus. I'm going to take the constant n outside of the integral from 0 to infinity of t to the n minus 1 e to the negative, what's that? E to the negative t dt. Okay? Okay, so, well, so here's the thing. Let's compute the value of the first, I mean, the upper minus lower over here. Okay, guys, did you guys agree that if we evaluate this quotient here for at infinity, remember from calculus 2, I mean, because I don't want to compute this limit, guys, using L'Hopital's n times. but at least we know the rate of growth of functions. And you guys agree the exponential grows faster than the polynomial? So at infinity, e to the infinity is a larger infinity in the denominator, so that's going to be a zero, okay? Now, what about zero evaluated at a polynomial? Isn't that zero divided by e to the zero, which is one? It's still zero. So this whole term, goodbye, goes to zero, all right, in one shot. Okay, so now let's talk about this the integral we have over here. Okay, so so this leaves us with, okay, hmm, with n integral from 0 to infinity of t to the n minus 1 e to the negative t dt. But do you guys recognize this integral? Doesn't that look like n gamma of n? All right, n gamma of n. Now, let me do a second iteration of this just to show you the pattern. Of course, I'm not going to be here forever doing these integrals, all right? So number two. Okay, let's say again by integration by parts, using integration by parts, I'm going to set u equals to t to the n minus 1. du will be n minus 1 t to the n minus 2 dt. Okay? Oh, come on, I can't write today. Dt. There you go. That means dv will be e to the negative t dt, and v again, negative e to the negative t dt. All right? Okay. So be careful. Be careful because, okay, actually, we can put a end of the proof symbol here, but I'm going to continue because this integral right here is being multiplied by n. So this will be equal to n times whatever we get from the integration by parts, which is u times v, that is negative t to the n minus 1 times e to the negative t evaluated from 0 to infinity already minus the integral from 0 to infinity of okay, v du, which is, oh, actually this is supposed to be n, not t, right? That'll be n minus 1, all right? uh t to the n minus 2 times e to the negative t, but there's a minus here. I'm going to put it over here, and then that's going to become a positive later on, right? Okay, so what is that going to leave us with? Again, guys, so I don't want to keep writing a bunch of terms. Do you guys agree that this is all going to go to zero again? For the same reason as before. So guys, subtracting one integer to the exponent, it's not going to change that much on the rates of growth in this case, right? For the function. So that's still going to be zero, okay? And that's dt, okay? So that's zero, okay, minus minus. That's going to leave us with n times, I'm going to take this n minus 1, integral from 0 to infinity, t to the n minus 2, e to the negative t dt. All right? Okay, guys. This is the same as saying n times n minus 1, integral from 0 to infinity, t to the n minus 2, e to the negative t dt. All right? I mean, do you guys see the pattern? Do you see the n minus 1? Do you guys agree that if I do a third integration by parts, I'm going to get the n minus 2, a fourth integration by part, n minus 3, and so on and so forth? This is good enough. So inductively, repeated iterations of integration by parts will produce n times n minus 1, n minus 2, n minus n minus 3, dot, 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 which is equal to what? N factorial. right? It's n factorial. So with this, we prove the two properties here. All right. Okay, let's use this. Okay, guys, you're not responsible for memorizing this derivation, although I hope it makes sense because all we're doing is using integration by part with symbols without numbers, all right? So I just want you to, I just wanted you to see the pattern of where is this coming from. Now, how about we use this gamma function? So evaluate gamma of 4 equals to gamma of 3 plus 1, all right? But because gamma of n plus 1 equals to n factorial, what's n here? N equals to 3. This equals to 3 factorial, which is 3 times 2 times 1 equals to 6. All right? Okay, let's fun and play with improper integrals. Evaluate the integral from 0 to infinity of x to the 7 e to the negative x e to the negative x dx. Do you guys feel like doing integration by parts 7 times? Even funnier. Do you feel like evaluating integration by parts 25 times? We're gonna do this in a blink of an eye. All right? Okay, check this out. Do you guys agree that this is the integral from 0 to infinity of x to the 8 minus 1 e to the negative x dx, which is gamma of 8, which is one number less 7 factorial. Whatever that number is, it's a really big number. It's not going to fit in the paper here, in the document. All right? But guys, notice for this first example on the integral, I took a moment to write the 7 as x minus 1 so we can relate it to the gamma function definition or with its integral form, right? Now, do you guys agree that 7, 7, those exponents are the same? So you guys don't have to set this integral anymore. Just identify the power of x. This is simply 25 factorial. That's all. And you bypass 25 iterations of integration by parts. And of course, I don't think the calculator is going to give you the result of that number. It's going to give you an overflow error. You might need maybe MATLAB, Python, or any computer system to actually compute that value. That's it. All right. How much time do we have? Okay, yes, we have plenty of time. Let me show you another definition involving the gamma function. Guys, this is the very introduction to the Laplace transform. All right, so the integral from 0 to infinity of x to the n e to the negative ax. Actually, what's the difference? This time we have not only e to the negative t. So we're coming up with a form where the exponential has a coefficient other than just -1. All right, let's prove this result. So the integral of x to the n e to the negative ax dx from 0 to infinity. Again, we're using integration by parts. I'm going to say, first of all, I'm going to do a change of variables. I'm going to do a substitution, guys, for a reason. T equals ax. This means x equals to t over a, right? This means from here, dt equals a dx, and dx equals dt over a, all right? So I'm going to replace this with the integral. I'm going to replace x with t over a to the n power e to the, what's ax? Isn't that just t? Negative t. These ways, so guys, we can just have everything in terms of t. Oh, dt or dx is dt over a. All right. Okay, so what do we have here? Oh, from 0 to infinity. Technically, I should set up the new limits of integration because we're going from the world of x to the world of t. But I mean, Infinity over a, it's still infinity. 0 over a is still 0. So the limits of integration are still the same. Okay, what is this now? So this will be the integral from 0 to infinity of t to the n over a to the n over e to the negative t over a dt. All right, putting these exponents together, this is equal to the integral of, I think it fits here. Okay, the integral from 0 to infinity of t to the n e to the negative t over a to the n plus 1 dt. And actually, this a to the n plus 1 is just a constant that can go outside of the integral. Integral from 0 to infinity, t to the n, e to the negative t, dt. But what's that? Isn't that the gamma function, right? Isn't that the 1 over a to the n plus 1 gamma of n plus 1? All right. And that's actually the result. What's this? But what's gamma of n plus 1? Isn't that n factorial over a to the n plus 1, which is this result? So now before we leave, yeah, we have time. Let's evaluate these two integrals right here using this consequence or this corollary, if you will, of the gamma function. All we need to do is identify n equals to 20 and a equals to 2. That's it. That's it. So so this is n factorial, that is 20 factorial divided by, what's a? Isn't that 2 raised to the 20 plus 1, which is 20 factorial divided by 2 to the 21st power. Don't even compute, just leave it like that. All right. I think you may end up getting a nice result anyway, but just leave it. Just leave it. Just want you to see how the gamma function works. All right. So n equals to 15 for part B and a equals to 3. So this is 15 factorial divided by a, which is 3, raised to the n, which is 15 plus 1, which is 15 factorial divided by 3 to the 16. Final answer. Final answer. All right. And I think this is a good place to quit.